Good morning. In this lecture, we will discuss about extension of a linear operator. First of all, we'll discuss about the equality of operators. Two operators T and S are said to be equal if they have same domain, and we write T is equal to be S if domain of a T is equal to be domain of S. That is, Tx is equal to be Sx for all x belongs to be domain of a T or is equal to be domain of S. So let X and Y be two norm-linear spaces and B be a subspace of X, and suppose that S is mapping from operator from B to Y and T is from X to Y are two linear mappings such that Sx is equal to be Tx for all x belongs to B. Now see that the following figure we have. Now in this case, this is the space X, this is space Y, and T is a operator mapping from this space X to Y, but where the S is an operator from a subspace of a space X, say this is a P, from B to this Y. So here, so we say that T is called an extension of the linear map S, and S is called the restriction of a T. If moreover the extension T is such that norm of T is equal to be norm of AS, then T is called an extension of AS with the preservation of the norm, that is the norm preserving extension. So here we will tell that if we go with this S, the S is called the restriction of a T, because here we have to be restricted a map from the subspace of AX to a Y. So we can say the restriction can be defined as let T be a mapping from domain of a T into Y and B be a subset of a domain of a T. We define the restriction of a T to be denoted by the T with respect to be a B from B to Y as T and restriction with respect to be B of X is equal to be Tx for all x belongs to B. So let T be an operator from domain of a T into Y and D of a T domain of a T is subset of AM. So an extension T is denoted by a T hat from M into Y such that T hat with restriction of a domain of a T is equal to be T and T hat of a X is equal to be Tx for all x belongs to be domain of a T. So now if domain of a T is a proper subset of X, then a given operator T has many extensions. So of the practical interest, there are usually those extensions which preserve some basic property. For instance, the linearity. If T happens to be linear or bounded, that is if domain of a T lies in a non-linear space and T is bounded. So the following important theorem is a typical in that respect. If concerns an extension of a bounded linear operator to the closure domain of a T such that extended operator is again bounded and linear and even has the same norm. So this includes the case of an extension from a dense set in a norm-linear space X to all of X. It also includes the case of an extension of a norm-linear space X to its completion. So now we'll discuss the following theorem, which is also the extension of this linear operator in non-linear space. So let T be an operator from domain of a T to Y, where it is a bounded linear operator, where domain of a T is a subset of AX, and X is a non-linear space, and Y is a Banach space. So here we have taken up the completion over the Y. So then T has an extension, say T hat, from closure of a domain of a T to Y, where T hat is a boundary linear operator of the norm. The norm of a T hat is equal to be norm of a T. So now we'll discuss the proof of this boundary linear extension theorem. So let X belongs to be a closure of a domain of a T. Then there exists a sequence Xn in a domain of a T such that Xn converges to X. Now since T is a linear and bounded, we have norm of a Txn minus the Txm, because the T is a linear, so this can be written as the T of Xn minus Xm. Now because here the T is again the bounded, so this is less than equal to be norm of a T into the norm of Xn minus Xm. So here the sequence Txn is a Cauchy because here it is being given at the sequence Xn is a convergent. So we have taken, because we have taken up the resistor Xn belongs to be domain of a T such that the Xn converges to be X. So now here the sequence is convergent. So here the sequence Txn is a Cauchy sequence. Sequence Txn is a Cauchy sequence, and we have already given that the Y is a complete. So the sequence Txn converges. And suppose that it converges to Y, which belongs to be capital Y. So define T hat by T hat of X is equal to be Y. Now due to the uniqueness of a limit, T hat is uniquely defined for all X belongs to be closure of a domain of a T. So clearly T hat here is a linear, so you can easily prove it out that the T hat is a linear because here the T hat X is equal to be Y. So we can go with the T hat of a alpha X plus beta, so we have a alpha 1X plus the beta 1Y, the corresponding elements from here, which is again we can prove it out that it's a linear. And T hat of a X is equal to be Tx for all X belongs to be domain of a T. So that T hat is an extension of a T. So now we use the norm of a Txn is less than equal to be norm of a T into norm of a Xn. Then Txn converges to be Y, where Y is equal to be a T hat of a X. Now since X maps to a norm of a X and the norm is a continuous mapping, so we obtain the norm of a Tx is less than equal to be norm of a T into norm of a X. So hence T hat is bounded and norm of a T hat is less than equal to be norm of a T. Also, because here T hat is an extension of a T, so the norm of a T hat is greater than equal to be a norm of a T. So being defined by supremum cannot decrease it an extension. So therefore the norm of a T hat is equal to be norm of T. It preserves the norm. So thank you, and these are the references that you can follow up.